We're going to start chapter 5 by talking about the graph of a polynomial function. We've already talked about two types of polynomial functions this year. We have discussed linear functions. Linear functions, you're going to see, is a type of polynomial function. We've also studied quadratic functions, and a quadratic function is also a polynomial function. You'll see that in just a minute too. So now we're going to look at other types of polynomial functions that have a little bit higher degree, another thing we'll talk about today. So let's start with some basic terminology. We'll start with a monomial. A monomial is a real number or a variable or the product of a real number and one or more variables with whole number exponents. The degree of a monomial is one variable. In one variable is the exponent of the variable. So an example of a monomial would be 5x squared. So a polynomial that has one term, mono means one, so a polynomial that has one term is called a monomial. 5x squared would be our example. A polynomial is a monomial or the sum of a bunch of monomials. So if we take a bunch of monomials and we add them all together or subtract, then we get what's called a polynomial. So like example would be 2x squared minus x plus 1. That would be a polynomial. Notice whole number exponents. Let's make sure we underline that up here. Whole number exponents. The degree of a polynomial, notice all these words are highlighted. The degree of a polynomial in one variable is the greatest degree among its monomial terms. So in the example I gave you, 2x squared minus x plus 1, the degree will be 2 because 2 is the greatest degree among its monomials. The degree, remember, is whatever the exponent of the variable is. So whatever the highest exponent is will be the degree of our polynomial. A polynomial with the variable x defines a polynomial function of x. So we can look at a polynomial function, which would be y equals a big polynomial, and the degree of the polynomial function is the same as the degree of the polynomial. So if I make it a y equals 2x squared minus x plus 1. So up here we have a polynomial. And then if I make it a y equals and give it two variables, then it now becomes a polynomial function. A function, remember, is always a y equals. Okay, so here's some more terminology here. The standard form of a polynomial function arranges the terms by degree in descending order. So highest degree down to lowest degree. So we put a polynomial in standard form. It's called standard form. Think about standard form of a quadratic, ax squared plus bx plus c. That's going to give us a polynomial in standard form. If the degrees are arranged in descending order, then it is a polynomial function in standard form. Where n is a non-negative integer, so our exponents have to be whole numbers. And notice this example that you are given has four terms. The 4x cubed is the cubic term. The 3x squared is called the quadratic term. The 5x is called the linear term. And the minus 2, is the constant. Remember, a number in math is a constant. So if it's a term that does not have a variable, let's make sure we know that. Constant term is the term with no variable. Okay. So we can classify a polynomial according to its degree, and we can also classify a polynomial according to how many terms there are. So if the degree is 0, 1, 2, 3, 4, 5, we can give it a name. If the degree of a polynomial is 0, we call it a constant. That would be like 5x to the 0, and we know that x to the 0 is 1, so it's just going to be a constant, 5. If the degree is 1, we call it a linear polynomial, and the example would be 2x minus 7. If the degree is 2, you can probably guess that it's going to be quadratic. And the example would be any quadratic polynomial that I give you. As long as the highest power is 2, then it is called a quadratic. If the degree is 3, these are the ones we don't know yet. If the degree is 3, we call it cubic. That makes sense, cubed, cubic. And the example would be, let's see, I'll make something up. X cubed minus 4x squared plus 2x minus 7. That's a good example of a cubic polynomial. If the degree is 4, it is called a quartic polynomial. And the example would be anything as long as the highest power is x to the 4th. And lastly, if the degree is 5, we can call it a quintic polynomial. A quintic polynomial, any polynomial as long as the highest power is 5. And anything bigger than 5, we just call it a polynomial. We can also classify a polynomial according to how many terms there are. If there's 1, 2, 3, or greater than 3 terms. One term, we already talked about this. One term, we have a monomial. If there are 2 terms, you might guess that we call it a binomial. And if there are 3 terms, you probably already know that we'll call it a trinomial. And anything more than 3 terms, we'll just call it a polynomial. Okay, so we can look at the examples now. Write each polynomial in standard form. We know what that means now. What is the classification of each polynomial by its degree and by the number of terms? So we're going to make sure that this polynomial is in standard form, and then we're going to classify it 2 ways. So I'm going to start with the term with the highest power and go down in descending order. So here's my polynomial in standard form, highest degree down to lowest degree. Also, I noticed that the highest degree is 2. Therefore, I'm going to call it a quadratic. And there are 3 terms in this polynomial, so I'm going to call it a quadratic trinomial. All right, let's do one more like that. Let's start with the highest power. So I see x to the 4th plus 10x cubed minus 6x squared plus 4x minus 12. So this polynomial has a highest degree that is 4. So I'm going to call this a quartic. And I see definitely more than 3 terms. Therefore, I'm just going to call it a quartic polynomial. Okay, that's easy enough. So we got some terms to remember. All right, the degree of a polynomial function affects the shape of its graph and determines the maximum number of what's called turning points, or places where the graph changes direction. So that's what a turning point is. Turning point for a polynomial function is a place where the graph changes direction. It also affects what's called the end behavior, or the directions of the graph to the far left and to the far right. So we're going to look at some examples and we're going to explore this. So describe the end behavior of the following polynomial functions. I'm going to show you how to do that, and you're going to use the graph to help you. We're going to look at our graph. How many turning points? We'll look at discuss how to tell where the turning points are and find the turning points using our calculator. So we have a lot to do here. So let's go ahead and start by putting this first example in our calculator. So I'm going to put in 4x to the 4th plus 6x cubed minus x. 4x to the 4th plus 6x cubed, look what I did, 4x to the fourth plus 6x cubed minus x. Okay, so I'm going to start in my standard window. And I see, let's see, maybe we'll zoom in a little bit. So I'm going to press zoom decimal, zoom 4. Okay, so now I can see a good picture of this graph. So I want you to notice a couple of things here. I want you to notice that in the middle, this graph has places where the graph changes direction. So if we read the graph left to right, then I see one turning point here, another turning point here, and another turning point here. So turning points are where the graph changes either from decreasing to increasing or from increasing to decreasing. So we know if the graph is going down, it's decreasing, and if the graph is going up, it's increasing. So I see, it looks like around negative 2, maybe the graph changes from decreasing to increasing. So that's a turning point. So we have one turning point, two turning points, three turning points in this graph. So this is typical of a polynomial function. In the middle of the graph, we have turning points, places where the graph changes direction. But then the end behavior that we're talking about in the instructions, the end behavior, it's what's happening at the far left and the far right of the graph. So that's what we're going to talk about first, the end behavior. So let's go back to the notes. The end behavior involves two sentences. The first sentence says, as x approaches infinity, f of x approaches infinity. So what that's saying is, as x goes forever to the right, because infinity is forever to the right, then f of x, which is the function, which is the y, remember, is going forever to infinity, which means going forever up. So as x goes forever to the right, so as the graph goes forever to the right, the function is going forever up. And so, but this is how we say it. We write as x approaches infinity, f of x approaches infinity. That's the first sentence. And we notice that on the graph, that as we go forever to the right, the graph's going up forever. And we also notice as we go forever to the left, the graph is also going up forever. Notice that as we go forever to the left, the graph is going up forever. So my second sentence needs to say, as x approaches negative infinity, f of x approaches infinity also. So this is saying as x goes forever to the right, forever to the left, remember the end behavior is what's going on the far ends of the graph. So that means as we go forever to the right, forever to the left. As x approaches infinity, as x approaches negative infinity. Forever to the right, forever to the left. What is the graph doing? It's going up forever in both directions. So that's what these two sentences is telling me. Okay, and then it asks about turning points. How many turning points? I see, what did we say? We said that there are 3 turning points in this graph, and let's talk about how we find them. So a turning point on a graph is classified as either what's called a relative minimum or a relative maximum. So let's draw a picture of what we think this graph kind of looks like. Let's see here. Okay, so it's doing something like this, isn't it? Where I saw 3 turning points. So this right here is a place where the graph changes direction. And a place where the graph changes direction is classified as either a relative maximum or a relative minimum. And if the graph changes from decreasing to increasing, then we call it a relative minimum. And if the place where the graph changes from increasing to decreasing, we call it a relative maximum. So we know that our calculator will find maximums and minimums for us. We learned how to do that when we did quadratics. So that's what we're going to do. We're going to use our graphing calculator and find the maximums and the minimums on our graphing calculator. So we're going to start with the one all the way to the left. The turning point all the way to the left is a relative minimum because at that point the graph changes from decreasing to increasing. So that's a relative minimum. So I'm going to do second calc and I'm going to do second calc minimum. and then I'm going to give it a left boundary and a right boundary. So I'm going to use my cursor and move to the left of the turning point and press enter, and then move my cursor to the right of the turning point, but not all the way to the other turning point. So it's got to be in between those two turning points. So it's got to be to the right of the relative minimum, the turning point here, but not all the way to this other one over here. So I'm going to press enter, and then when it asks me to guess, remember, you just press enter again. And then it gives me my minimum. Remember, the minimum has two parts. It's an ordered pair. So remember, the minimum is negative 1.0, let's round to 3 decimal places, negative 1.037. Where does the minimum occur? At x equals negative 1.07. So we're just going to give it as an ordered pair for now, and we can talk more about it. So I'm going to say negative 1.070, comma, negative 1.037. Okay, so there's one turning point. Now let's find the next turning point. So we're going to go to the next turning point right here, this relative maximum, right in the middle, the place where the graph changes from increasing to decreasing. So I'm going to do second calc maximum. And then it asks me for a left boundary and a right boundary. So I'm going to move my cursor on the left side of the maximum that I'm finding, but I don't want it all the way over here to mess up with this minimum here. So I want the left boundary right about where I am now. Press enter, and then move your cursor to the right of the turning point, but not all the way to the other turning point. So just kind of in the middle of those two, and press enter. And when it asks me to guess, you press enter again, and then it gives me that relative maximum, negative 0.270, comma, negative 0.173. Was it negative? Positive. Positive 0.173. Okay, and we've got one more turning point to find, so we're going to practice again. Now, this last turning point here is a relative minimum because at that point, the graph changes from decreasing to increasing. So I'm going to do second calc minimum and move my cursor to where it is on the left side of the minimum, but not all the way interfering with those other turning points. So press enter, and then move your cursor to the right of the minimum that you're finding. Press enter again. When it asks you to guess, you press enter. And there it is. So it's 0.216, comma, negative 0.147. Okay, so that was good practice finding turning points, finding maximums and minimums. So remember, we've got several things you have to know here. First thing is, what is the end behavior? How do we describe it? As x approaches infinity, what is f of x doing? It's either going to infinity or negative infinity. And then as x approaches negative infinity, f of x will either be approaching infinity or negative infinity. So you've got two sentences to write, just like what I just wrote. We're going to do this one more time, don't worry. And then I've got to use my calculator to determine how many turning points and what are they. Okay, let's do the next example, the quadratic. I'm going to go to my calculator, negative x squared plus 2x. Negative x squared plus 2x. And I'm going to look at the graph, and I expected to see a parabola. There it is. So let's describe the end behavior. I see, as we go forever to the right on this graph, in other words, as x approaches positive infinity, looks like the graph's going down forever. So when the graph's going down forever, you're going to say f of x approaches negative infinity. And it looks like as x approaches negative infinity, which means as we go forever to the left, it looks like this graph is also going down forever. So as x approaches negative infinity, the function is also going down to negative infinity. So these are the sentences we write. We write as x approaches, the arrow means as it approaches infinity, f of x approaches negative infinity. And that's because as we go to the right, the graph's going down forever. And the second sentence, as x approaches negative infinity, f of x approaches negative infinity also. So those are the two sentences. Notice they look exactly the same as the ones before from the last example, except the last example, both ends were going up forever. So we said f of x was approaching infinity both times. And then this time, both ends of the graph are going down forever. So we'll say f of x approaches negative infinity. And let's look back at the graph. I see one turning point, one place where the graph changes direction. Let's find it. Since the graph changes from increasing to decreasing at this turning point, we'll say that it is a relative maximum. So I'm going to do second calc, maximum. And left boundary, press enter. Right boundary, move your cursor to the right of the turning point, press enter. I'm going to ask you a guess, press enter again, and we're going to say that's 1, 1. So I'm going to say there is one turning point, and it is 1, 1. Okay. We're going to move on a little bit, and we can come to finish these other two tomorrow together. Determine the sign of the leading coefficient and the least possible degree for the graphs. Okay. The sign of the leading coefficient. Let's see. The sign of the leading coefficient will tell us what our end behaviors are doing. If the sign of the leading coefficient is positive, then that means, let's write positive, that means as x approaches infinity, f of x approaches infinity. So as we go to the right forever, the graph will be going up. And if the leading coefficient is negative, then as x approaches infinity, f of x will be approaching negative infinity. Which means that as we go to the forever to the right, the graph will be going down. So I'm looking at both of these graphs, and I see that as x approaches infinity, the graph's going up forever, both times. So that means that the leading coefficient for both of these examples, leading coefficient for both of these examples is positive. And then there's one more little rule, that the graph of a polynomial function of degree n has at most n minus 1 turning points. Let's read that again. The graph of a polynomial function of degree n, so whatever the degree is, n, has at most n minus 1 turning points. So like if the degree is 3, then there will be at most 2 turning points. If the degree is 2, think about a quadratic, 1 turning point. If the degree is linear, 1, if the degree is 1, there will be no turning points. So when I see this first example, I see 2 turning points. So 2 turning points means the degree is at least 3. And in this one, I see 1 turning point. So that means the degree is at least 2. But let's think about that. This, if the degree was 2, then it would be a parabola, wouldn't it? If the degree was 2, it would be quadratic, and our graph would be a parabola. And we know that parabolas are symmetric. And I do not believe that this graph looks symmetric about an axis of symmetry. So therefore, I'm going to change it and say it's at least 4. How do I know it's 4 and not 3? Because one more thing, and then we'll stop. The end behaviors also determine the sign of the degree. The sign of the polynomial of the degree. If my in behaviors are different, then the degree will be odd. So let's write that down too. Odd degree, different in behaviors. Even degree, like for example 2 or 4, then the in behaviors will be the same. So for the first example here, I know the degree is odd. And since I see 2 turning points, then there has to the degree must be at least 3. And for the next one, I know the degree is even because the in behaviors are going in the same direction, both up. So odd degree, one in behavior will be going up, one will be going down. And even degree, both in behaviors will either be going up or they will both be going down. So that's how I knew the degree was at least 4, and I knew it couldn't be a 3. All right.